Hi, welcome to the start of a new unit, Unit 4 here, and this is Lesson 4.1. This is Intro to Randomness and Probability. So the idea is that we live in a world where things are very, very random, and our job as statisticians, or future statisticians as we graduate through this course, is to really try to better understand that randomness, and that all starts with understanding probability. So the first thing we want to talk about is chance behavior in the long run. Now, a chance process is any situation where the outcome is unknown. So if you could think of anything that you encounter in your daily lives where the outcome is unknown, that is considered what we call a chance process. So the process of going through something and you're not quite sure what the outcome is going to be, that's a chance process. And the cool thing that we're going to learn here is that chance behavior is unpredictable in the short run, but it is a very regular and predictable pattern and in the long run. So the idea is that when you're working with a chance process, you might not know in the short run, and on a very few attempts of that. So if you're playing a game and you don't know the outcome of the game, and then if you only play a couple games, the outcome could be all over the place. It could be very, very unpredictable. But most chance processes, if repeated over and over and over and over again, in the long run, we actually can see some predictable patterns forming. The idea of that concept is the basis of probability. So here's some examples of some very, very simple chance processes that we experience. Tossing a two-sided coin. Every time I toss a coin, I do not know the outcome. I know that it could be a head or it could be a tail, but when I toss that coin, I do not know the outcome. And the idea is that, as we just talked about, in the short run, trying to guess the outcome on maybe just 5 tosses, it's very unpredictable. You could get 1 tail, 2 tails, 3 tails, heck, you can get even all 5 tails, you could even get no tails in just 5 tosses. But if you toss that coin a large number of times in the long run, tossing it and tossing it and tossing it, we all know that in the long run we expect 50% tails and 50% heads. Rolling a 6-sided number cube, which we know is a die, that is also a chance process. Every time I roll that die, I don't know what's going to happen. It's either going to be a 1, a 2, a 3, a 4, a 5, or a 6, but I don't know what's going to happen. And I can get the idea that if I toss that die only a couple times, who knows what's going to happen. The probabilities could be all over the place, but in the long run, after tossing that die many, 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 many times, I will start to see a pattern forming. And that's the idea, and that we're going to explain in this video. Another example is if you have a jar that contains 10 marbles. Some are blue and some are red. Again, every time you reach into that marble, or you reach into that jar, the color you pull out is a chance process, right? Because I don't know what color I'm going to get. I might get a blue one, I might get a red one. I'm not quite sure the outcome. That is another example of a chance process. All right, so we have 2 different kind of types of probabilities, and the first type is experimental probability. The easiest way of understanding experimental probability is you actually do it. Experimental probability is you sit there and you actually flip that coin, you roll that die, you start picking out marbles. So here we explore the outcome of an event in a certain number of trials. As we toss a coin, we record the side facing up after each toss. So what we have here is what we call a probability model, right? So on the left side here we have the proportion of heads, because that's what we're looking for. We're looking for heads. And on the bottom here we'll have how many tosses, and we're going to track the probability basically. So maybe we have on our very first trial, we toss it and we do not get a head, right? So far we are 0 for 1. So that means the probability after 1 toss is 0.0. That's the proportion, right? 0.0. Then after 2 tosses, or on the the second toss, we do get a head. So right now we are 1 for 2. We've had 2 tosses and one of them has been a head. So now we have flown up after 2 tosses. We've flown up now to 50%, because 1 out of 2 is 0.5. In 3 tosses, well, once again we don't get a head. So now we are only 1 for 3. So now we drop back down to 33%. So somewhere right around here. So the idea is that the probability or the proportion of heads is fluctuating, right? It's bouncing around. And maybe after 10 tosses, I see 4 out of 10 have been heads. So now after 10 tosses, I'm at 0.40. But I've been fluctuating. That's the idea. Is in the short run, you're fluctuating all over the place. But as you toss that coin more and more and more, that true probability will start to settle in at the true value, the true probability, the true proportion of heads. The idea is that we know, and we'll talk about this shortly, we know that when you toss a coin, there's a 50% chance of getting a head. But if you only throw it 10 times, you might not see 5 out of 10. For example, we did it here and we saw 4 out of 10, which is 40%. So in the short run, which 10 tosses is clearly the short run, it's not a surprise it's unpredictable and we saw 4 out of 10. But as we toss that coin more and more and more, we should start to see the true proportion of heads settling down at that true value of 0.5. Now, theoretical probability, here we don't actually toss a coin at all. We use some common sense and what we know about the coin or die to think about what we expect to happen in the long run. This is the simple idea that you guys have probably heard before. Okay, you know that when you toss a coin, there are 2 outcomes, head and tail. One of those outcomes is a head. Therefore, the theoretical probability is 0.50 or 50% to get a head. So if we're trying to find the probability that we get a head, we know that in the long run, it's going to be 1/2, 50%. That's the theoretical probability. I didn't flip any coins to figure that out. I just thought about outcomes on the bottom, 2 outcomes. One of them on the top is going to make me happy because it is getting a head. Now, this idea is known as the law of large numbers, right? Theoretical probability is based on the law of large numbers. And it sounds like a kind of a funny law, but it really is. It's called the law of large numbers. And the law of large numbers states this: if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. We call this single value the probability of the event occurring. So the idea that I'm trying to emphasize here is that the probability of an event occurring is not found in the short run. The probability of an event occurring is not found after tossing a coin 10 times. Because if you toss a coin 10 times, you know what? The outcomes are, they're very, very unpredictable. I mean, we would assume that we would get 5 heads, but we might not. We might get 6, or we might get 7, or we might get 4, we might get 3. That's because it's only 10 times, and that's not the long run. The true probability of an event occurring will only reveal itself to us after we start tossing that coin 1,000 times, 10,000 times, 100,000 times. Then and only then should we start to see the true probability settling in at the theoretical value that we know, 0.50. Now, the probability of any outcome of a chance process is always a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So, a lot of kids don't understand that. Like, they've never looked at probability through this lens, but you need to for this course. So I'm going to read that one more time. The probability of any outcome of a chance process is a number between 1 and 0, or 1 and 0, or 0 and 1, that describes the proportion of times the outcome would occur in a very long series of repetitions. Now, let's give a quick example here. We all know the probability of getting a head is 0.5, right? Now, first off, that is a proportion which you could change to 50% if you would like. This means in the long run, after a very large amount of trials, we would expect 50% of tosses to be a head. Okay? What kids misunderstand is that they think, oh, toss a coin 10 times, you're going to see 5 tails. You're going to see 5 heads. Toss a coin 100 times, you're going to see 50-50. No, you will not. That is not predictable at all. What we do know is in the long run, and there's no estimate, I mean, you could say infinity if you want, in the long run, only after a very large amount of trials, then and only then would we actually expect 50% of tosses to be heads, which would imply 50% to be tails. All right, now let's also think about the probability of rolling a die and getting a 6. Getting a 6. Now, let's think about this theoretically. There are 6 outcomes when you roll a die: a 1, a 2, a 3, a 4, a 5, and a 6. One of them is a 6. So the probability is 1/6, which would be, as a decimal, it is 0.166 repeating. So I'm just going to round that to 0.1667. I'll round that last one off. And what this means is that It doesn't mean that if you toss the die 6 times, you're going to get 1 6. We all know that that's not true. That's not what's going on here. So when we talk about the probability of getting a 6 to be 0.1667 or 16.67%, what we mean is that in the long run, if I toss that die many, 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 many times, only then, after many, many, many tosses, many, many, many trials, only then will I expect to see 16.67% of those many tosses be a 6. So probability has nothing to do with the short run. It's all about the long run. Things in this world only become predictable in the long run. All right, here's an example with my jar with blue and red marbles. What is the probability of getting a blue marble? Now remember, we have no idea how many blue marbles there are. So how could we figure it out? Well, start picking out marbles. But you got to make sure you replace them. This is going to be something that's important for the rest of this unit. Here we want to make sure that if I want to keep the probability consistent, I have to put the marble I take out back into the jar before I take another one out. Because if I start taking marbles out of the jar, the probability is going to change because there's less marbles in the jar. And if I eventually take all the blue ones out, well, then I have a 0% chance of getting a blue one. So I've got to make sure I replace those marbles back in. So the idea here is that if I just do trial 1, right, and I get a red marble, I'm 0 for 1. So after one trial, I'm at 0%. Second trial, I get another one red. I'm 0 for 2, so I'm still at 0%. Third trial, I'm now got a blue one. All right, so I'm 1 for 3. So I'm just tracking what has happened over time here. I'm tracking the proportion of blue marbles. Now 1 for 3 makes a jump to about 33%. Okay? Oh, I kept my dot in the wrong place there. So the idea here is that it's fluctuating, right? So again, if I keep doing this over and over again, even after, say, 20 trials, maybe after 20 trials, I have seen 7 out of 20 blue marbles. Okay? That's 35%. So now I'm at 35% here. But the idea is that this is going to fluctuate. It might heighten, it might lower. But it's never going to settle in to the exact probability until I do this many, 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 many times, right? So let's just now go ahead and reveal that maybe the truth is that there are 4 blue marbles, and we all know that if there's 10 marbles in that jar and 4 are blue, then the probability of getting a blue one is 0.40. But that 0.40 will only start to reveal itself and settle down after a large number of trials. So it might take over 100, maybe 200, maybe even 1,000 trials for me to really start to see that 40% number becoming solidified. So it might bounce to 41, to 39, to 41, to 39, to 42, to 38. It might bounce a little bit, but only in the long run will I start to see it settle in at that 40%. All right, let's discuss a couple probabilities here. Now, it is important to remember that probabilities are always between 0 and 1, and then you could change them to a percentage if you would like after that, but they are the proportion of times that something happens in the long run. So if something happens 0, it'll means it'll never happen, right? If the probability is 0, that is 0%, it will never happen. It means that you could sit and toss that coin, roll that die as much as you want, you're never going to see it happen. A 1 means it always happens. 1 represents 100%, so it's always going to occur. Now 0.01 would be 1%. This is very unlikely. This means it's only going to occur 1% of the time in a very large number of trials. So only in a very large number of trials will you ever see this thing occur 1% of the time. All right, 0.3 would be 30%. Now I know there's no 0 there, but if you move the decimal twice, the 1 will be created, so 30%. 30%, some students will start to think that 30% is low. 30% is pretty likely, right? I mean, if something has a 30% chance to happen, it means it's going to happen 30 out of 100 times in the long run, 30%, right? It doesn't mean if you do 100 tosses or 100 trials, it will happen 30 times. It's the idea that in the long run, we will see 30%, and that's actually pretty likely. That means it, definitely could happen. Now 0.98 is 98%. This is extremely likely, right? This is like, it's definitely going to happen. Obviously, there is still a chance it won't happen, but 98% means over the long series of trials, you're more than likely going to see this happen quite a lot. Okay, so make sure you just kind of understand the basics of probability there, the idea that it's between a number 0 and 1. You can't have a negative probability, nor could you have a probability over 1 or over 100%. All right, the last thing I want to make sure we talk about here with probability is don't ever believe what's called the law of averages. The law of averages deals with when you're working with people and somebody says, oh, that guy's on a hot streak. Okay, hot streaks don't, those don't really exist in our world of probability. For example, if I'm rolling a die and I get a 4, and then I roll it again and I get a 4, and I roll it again and I get a 4, and I think, oh my goodness, something's going on here. The die is hot, the die is warm, the die is going for a 4, and there's now an increased chance of me rolling a 4 because I've rolled so many 4s. Absolutely not. Dies do not have memories. That die doesn't know what's happened before or what will happen next. It's a die. So there's no such thing as a hot streak. Or the same thing with the cold streak. Okay? It's not like if you toss a coin and you're looking for a head and you get a tail 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 and you're thinking, oh man, I'm never going to get a head. Looks like the probability of getting a tail is increasing. The probability of getting a head is decreasing. No, there's no such thing of that happening, right? Things don't average out. Those coins, those die, they do not have memories. They just know that every toss, something new could happen, okay? Be careful with your working with people. Because, for example, baseball players, they are known to have hot streaks and cold streaks. Well, they're baseball players. They could improve. They could also have slumps where they get down on themselves. Their emotions make them bat worse. Okay, same thing with basketball players. Maybe you get into a shooting slump. Well, that's because you're working with people, right? When you're talking about shooting a basketball, it is a chance process in the sense that you don't know if it's going to go in or if it's going to miss. But at the same time, there's a lot of skill involved in shooting a basketball. So it's not so random as tossing a coin or rolling a die. Okay, so hopefully that makes sense. So when we talk about a basketball player's free throw percentage, that is his percentage of shots made after a long series of tries, which makes sense. It definitely has some connection here to this idea of a long series of outcomes will produce that true percentage. But we don't say, oh, this guy's got a 68% probability of making that shot. That's the general idea, but players have emotions. Players have minds. And sometimes they can get a cold or hot streak, but that's with people. Okay, when you're working with true chance processes, we do not have these hot or cold streaks at all. Okay, so make sure that you understand that when it comes to probability. Okay, that's it for this lesson.